Start with? Which one? 4. So let's look at number 4. Okay. So today, okay. And number 4, we have limit Sx approaches 0 from sine 3x times sine 5x divided by 7x squared. L'Hopital's rule works here, but it's not recommended because there is a much easier way, which is limit when x approaches 0 is the same with 3x approaches 0 is the same with 5x approaches 0. So I have sine 3x 1/7 in front over x and times 5x over x. So I split 7x squared into 7 times x times x. Why? Because I know this result that if I put a 3 here, then I have to put a 3 at the top. And if I put a 5 here, I have to put a 5 at the top. And I know that this will approach 1. This will approach 1. And then I have 3 times 5 over 7. So this is what I was hoping to see. You didn't have to go into anything extensive because differentiating the product, you have to be very careful. It's a product of sine, which will take you a long time, the second time, to differentiate. So I don't recommend that route for this problem. You will eventually get it, but it will take a long time. Good, that was number 4. Anything else you would like to see? Which one? Number 6. 4, 5, 6. Yes. Several of you had difficulties with this, and I wasn't sure why. So this is problem 6. So x sine y plus cosine x equals y to the third. So when we differentiate the left-hand side and the right-hand side, the left-hand side has a product, so we have to be careful there. And then the right-hand side is a power, so it's a function to the third power. So the left-hand side, x times sine y, so x prime is 1 times sine y plus x times sine of a function prime is cosine of that function times the inner function prime. Plus, I should write minus, so this is minus sine x equals 3y squared dy over dx. Is this clear so far? Do we understand each step? Yes? Sorry about that. So, is this okay? So, remember, I'm after this. So, first I will move this to the other side. So, I have sine y minus sine x equals 3y squared minus x cosine y, and I factor out dy over dx. Is this okay? And finally, dy over dx is this over this. Sine y minus sine x over 3y squared minus x cosine y. I was pleased to see that many of you raised your grades. The Kabul, I was expecting to see better results, but it's okay. As long as the next 2 tests are good grades, you have nothing to worry about. I did see 3 students worked hard and they raised their grades, so I was very happy to see that. It's all about time and the amount of time you spend on this. Okay. Like before, I would like to add a couple of points to your test grade, so you can do 5 problems again from this test using Maple, and turn them in. And I will add 5 points. Anything else? Yes?
Number 3.
Yes. Number 3. What was number 3 all about? So we have f of x equals x squared minus 1 squared e to the x. So here, if you did not recognize and you did not use the product rule, then I could not give much credit. So this is function 1, and this is function 2. So therefore, f prime of x equals 2x squared minus 1 times 2x times e to the x. This is just 1 prime plus x squared minus 1 squared times e to the x. So this is 2 prime. Now be careful, I still saw the wrong formula for the quotient. You wrote 1 times 2 prime minus 1 prime times 2. It's unacceptable. One more time. I'm going to finish this up, but I just remember that and I don't want to forget. So if I see this, like 1 times 2 prime minus 1 prime times 2 over 2 squared, I cannot give credit for it. So it's unacceptable at this point in time not to know the quotient rule. Please. Please.
Why is it not?
Because it's 1 prime times 2 minus 1 times 2 prime. They are reversed. It's 1 prime times 2 minus 1 times 2 prime.
You can't do it.
No, you cannot. No. No. They flip inside the product, not these two, not the terms. The terms are flipped here. Inside the product, it's fine. But this cannot be on the second spot with minus in front. This has to be on the first spot, and this has to be on the second spot. And this has to be positive, and this has to be negative. Okay, so I'm coming back to the problem 3. So what I did here, I factored out e to the x, and I factored out one of these two, right? So I have x squared minus 1 e to the x. That's my factored, the common factor. E to the x is out, and one of these. So this is 4x. E to the x is out, and one of these. So plus x squared minus 1. This is extremely important. We do this a lot in pre-calculus. So x squared plus 4x minus 1 times e to the x. So in order to determine what was the point 1 comma, what was it given? It was given 1 comma 0. So in order to determine the equation of the tangent line, I have to find f prime of 1. But f prime of 1, it turns out to be 0. So then I have y minus y1 equals the slope times x minus x1, where this is 0, this is 1, and this is 0. So then y equals 0, which is the horizontal, which is at the x-axis, horizontal line, is the equation of the tangent line to the graph of the function at the point 1 comma 0. Anything else? Is there anything else you'd like to go back to?
1f.
1f. What did 1f say? It should have been e, not f, but I'm sorry about that. So y equals hyperbolic sine squared of hyperbolic cosine. So first of all, I have a power on sine, hyperbolic sine, and then I have a function inside sine. Is that okay?
Yeah, I thought they were multiplied.
Well, this one doesn't have an argument. This is just the name of the function. So this must be the argument. Is that clear? If this happens on the next test, ask me, okay? If you have any doubts. So this is 2 times hyperbolic sine of hyperbolic cosine times sine prime, which is hyperbolic cosine of hyperbolic cosine times, right? So 2 times sine prime times cosine prime, which is times hyperbolic sine. Now, when I saw in something like this, if I saw somebody putting a plus and having 2 terms, that has to be addressed quickly. But now I understand, so you looked at it as a product, that's why. Okay, but remember the argument is not there. This is just the name of the function. So this must be the argument. Yes, I put all the handouts on them. Yes.
Are you finished with this?
Yes, I am.
So it's the derivative of the outside times the inside times the derivative of the...
So first of all, we have several steps. We have the power. We have a function, and we have a function inside of that function. So the power comes in front. I subtract 1 from the power. So it's power 1. So this is 1. Now I differentiate this function, and I get this. And now I differentiate the inside function, and I get this. So there was no point in...
This is the power
and the chain rule together. So we are not asked to... I saw a couple of you went back to e to the x minus e to negative x. There is no need for that. I'm not saying it's wrong, but that was not what the problem was asking. Good. Next question. 1c? Yes, I no longer have a test. I'm so sorry. Can anyone dictate 1c?
y equals raised to 3. The thing is e raised to 10 squared x.
That's it, right? Okay. So now let's talk about the layers here. A layer, the outside is 3, power 3. Then I have cosine. And then I have e to u. And then I have u prime. So power 3, and then cosine, and then e to u, and then u prime. A lot of steps. So then y prime equals 3 cosine squared of e raised to tangent times cosine prime, which is negative, sine e to tangent squared, times e to tangent squared prime, which is e to tangent squared, times the inner function prime, which is tangent squared prime, which is 2, times tangent x, times the inner function prime, which is secant squared x. Although I said don't simplify, I would have just presented in one more step, the minus, the 2, and the 3. So negative 6 cosine squared e to tangent squared times sine e to tangent squared times e to tangent squared times tangent x times secant squared. But if you stopped here, I gave full credit. That's fine too. Good. Anything else? Is there anything else that you would like to go back to?
Do you get extra credit?
Yes. Yes. Now, I hope you agreed that I couldn't find anything easier than that. Some of them are really long and a lot of work. So we had, if I remember correctly, we had this, and we had dy over dx. It was decreasing. So when it says decreasing, you have to consider it negative. So we were asked to find, I'm sorry. So we're asked to find dx over dt. Right? Is that what the problem was asking?
Yeah.
Okay, so you either solve, I solved, for example, or not, I solve for one of the variables. It doesn't matter. So let's say I'm solving for x. A divided by y. So then I have dx over dt equals negative 8 over y squared dy over dt. So far so good. All I have to do is just plug in when dy over dt is this. So, and y was, I don't remember, what was 2, thank you. And dy over dt equals negative 3. So then from here, I have that dx over dt equals negative 8 divided by 2 squared, which is 4, times negative 3. So this is negative 2 times negative 3 is 6 centimeters per second.
We actually found a 9 quickly.
Yes, what does it say?
Use differentials to estimate sine of 89 degrees.
Yes. Sine of 89 degrees is approximately f of x plus f prime of x times dx. So I have to consider f of x to be sine x, x to be 90 degrees, and dx to be negative 1 degree changed into radians, negative pi over 180. Nothing in calculus, almost nothing in calculus can be considered in degrees. So then from here, this will equal sine 90 degrees. I forgot to write f prime of x, which is cosine x, plus cosine 90 degrees multiplied by negative pi over 180. And then you get an approximation. Anything else? Anything else? Number 7, what does it say?
Use logarithmic operations to define the derivative of y equals tan x raised to x.
Very good. So we have natural log y equals x squared times natural log of tangent x. So when I differentiate natural log y, I have 1 over y times dy over dx. And here I have a product of two functions. The first function prime is 2x times natural log of tangent x plus x squared, and I differentiate natural log, which is 1 over tangent x times secant squared. So all I have to do is multiply by y. So then dy over dx equals tangent x raised to x squared, and you didn't have to do anything here. So 2x natural log of tangent x plus x squared secant squared over tangent x. Is this clear?
What happens to the 1 over y?
I multiply both sides by y. This is y. Because I'm solving for dy over dx, I have to multiply both sides by y. Okay, anything else? Yes, Thomas?
You do number 2e.
2e. Can I look at anyone first? What was 2e?
2e.
2e. So that's 2.
Oh, that's good.
Yeah, the total distance. So depending on what you did on the previous step, so the total distance is the absolute value of, I don't remember, it was between 0 and 1 and 1 and 2, right? So we were asked the total distance between 0 and 5. So s of 1 minus s of 0 plus, was it S of 2 minus S of 1, and plus S of 5.
S minus S.
No, I'm jumping here. It's not possible.
No, let's do.
5 minus 2. So this is
Both
3
have
here.
three.
So this is 3 here. Okay, okay, then it works. So you have to plug them in the function. Can anyone give us the number so I can put them in?
It's 4 minus 0.
4 minus 0.
4 minus 4. 20 minus 0.
Thank you. So this is 4 plus 4 plus 20, 28. And it was in meters. Is that good enough?
Oh, shoot. 4 plus 20. Oh my god, I already did that, but I
I'll take a look at it. Just don't write anything and show it to me.
And what about G?
And is it the same problem?
Yeah.
So what does G say?
Because the particle speeding up and then slowing.
Yeah, you have to present the sign for the velocity and the acceleration, and you will see what happens there. So the velocity was 0 at 1 and 3. Am I correct?
Yeah.
1 and 3. So that's t. 0, 1, 3, infinity, and the velocity and the acceleration. The acceleration was 0 at 2. So this was positive, I think. Was it? And negative? Am I correct? Or the other way around? Okay, and this was negative, right? So between 0 and 1, they are going against each other, so it's slowing down. Between 1 and 2, they're speeding up because both vectors are going in the same direction. Speeding up. Here again, they are slowing down. The particle is slowing down because the velocity and the acceleration are working against each other. And from that point on, it's speeding up. This is a much better setup and summary than just graphing. I think it's much better to present the signs of the velocity and the acceleration when the two vectors are working together. Even if it's in this direction or this direction, the particle is speeding up. But if they are working against each other, either like this or the other way around, then the particle is slowing down. Good. Anything else? Anything else? I'm still working on a summary for chapter 3 that I will have ready for you. So when we start reviewing, and every now and then I like to go back to those. So if you don't have anything else from me, I would like to start chapter 4. We have 2 more chapters and not much time left. We have roughly about 6 weeks. Yes?
That's actually something I was going to ask is either today or on Wednesday, can we have like maybe a tentative like schedule of what days we're going to be doing which sections and whatnot?
I'm not sure.
Okay.
Because if students have questions, I have to stop. If I can't really say how much. I mean, I would like to accomplish 3 sections today, but I won't. But I'll do as much as I can. And then maybe at the end of the day today, I will have a better idea. But I can move on if students have questions. I can do that. Okay, so before we talk about and we look at this handout, I would like to say that chapter 4 deals with applications of what we studied so far. And you can say, but we already looked at applications. And I would have to say, yes, we did. We already looked at applications. But this is in depth more, I would say. In pre-calculus, I say to my students, we are limited in graphing functions. But here we are not limited. We don't even need to use the graphing calculator in order to graph a function. We will do absolutely everything by hand. And you can see what's the use of that. Well, you may not need to do it much later beyond Calc 2, but it will show you how powerful calculus is. We will be able to graph everything we want by hand. Everything. Yes, the work is going to be extensive, but that's one application. And then there are many more applications later. In Calc 2, we'll look at areas and volumes. We're going to rotate areas to get volumes and much more. Okay, in Chapter 4, as I said, applications of differentiation. So the first application, the first thing that we will look at in 4.1 are max-min. And we will relate this concept to what we covered so far. So we want to find a max or a min. There are two different types of max and two different types of min. So for example, if I have a graph, let's say that starts here, and let's say it does this. For now. Well, obviously this point here is the minimum. And it's of two types of minimum. It is local. Well, why is it called local? Because I can show an open interval, and the open interval has to be on both sides, not just on one side. I can show you an open interval around that point where all function values are bigger than that one. So that's why this is a local minimum. It is also called a relative as well. We will go back and forth, local and relative. They mean the same thing. It's also a global or absolute for this particular function because there is nothing lower than it. For the entire function, there is nothing lower than that point. So this value right here, I'm going to say 1. And the location, let's say, is 7. So where is this local minimum and absolute minimum when x is 7? How much is it? 1. Endpoints of the interval can never be local or relative. So this one is absolute or global max, but is not a local max. Why? Because I cannot show you the open interval on both sides, because the function is not defined on one side. So that's why this point is only the absolute max. So where is it? I'm going to say at 15. How much is it? I'm just picking some numbers. So where is the absolute maximum? Where? When x is 15. How much is it? 10. Also, this point is nothing. It cannot be local, because I cannot show the open interval on both sides, and it cannot be absolute max, and it cannot be absolute min. This is the absolute min, and this is the absolute max. So this point is nothing. Okay, now how do I determine a point like this? How do I find it? How do I find this point? How do I find this point? And then we can go back to the handout and I'll explain, and we'll fill out the handout in a second. So how do I find this point? My starting point is something called critical number. What does a critical number represent? What does a critical number represent for a function, of course? What does it say about the function? What does it give? A critical number gives a max or a min, potentially. But something has to happen there. So this critical number can turn into a max, a point, an x value at which the maximum exists, or can turn into a minimum. How do I know which one it is? I'll show you in a minute. But what is a critical number? A critical number comes from two possible sources. One source is when f prime of that c, I'm going to call c the critical x value, critical number, is 0, or when f prime of c is undefined, comma, this is very important, but f of c is defined.
Is that possible?
Absolutely. Very good question. Let's think of the square root of x. The square root of x has domain what? Excellent question. What is the domain of the square root of x? The square root of x. Greater than or equal to 0. Now differentiate the square root of x. What do you get? 1 over 2 the square root of x. What is the domain of 1 over 2 the square root of x? Definitely not 0. So 0 is a critical number because f prime is undefined, but f of x exists at 0. That's one of the simplest examples that I could come up with right away, in a second. Okay? So I'd like to come back to the handout. So absolute max, absolute min, local extrema of a function. So when we talk about max and min, we talk about extrema. Extremum is the singular, extrema is plural. So when we talk max, min, we talk about extrema. A function can have extrema, or can have just max or just min. And critical numbers. So I like to jump to critical numbers first, and then we'll come back to the rest. So C is a critical number of f if C is in the domain of f, in other words, f of C exists, and if prime of C is 0, or if prime of C does not exist. So that we established. And I would like to find the extrema for this. And before extrema, I would like to find some critical numbers. And we'll come back to this in a minute, promise. So let's find critical numbers for these functions. Please choose. You may, since there are two polynomial functions, let's do just one. This will take us a while because it's a trig function. We can, of course, and we should do this. So choose a polynomial function, and the radical, and the trig function. I'm sorry? A. Okay, very good. So let's start with A. We're given f of x is 3x squared plus 12x minus 4. And which page am I on? 7. Good. So for this function, I'm asked to find critical numbers. I know critical numbers come from two sources. From f prime of x being 0, and from f prime of x being undefined. Of course, when f of x is defined. Okay. So then, in both cases, I have to find f prime. So when I find f prime, I get 6x plus 12. I set f prime of x being set equal to 0, and I get x equals negative 2. X equals negative 2 is the only critical numbers of f of x. How come? Because f prime of x is defined everywhere. 6x plus 12 is defined everywhere, so there are no critical numbers coming in this case for this function coming from f prime being undefined. Okay.
Can you run through that one more time?
I find the derivative and I realize that it can never be undefined, so no critical numbers come from this source. But critical numbers come from f prime of x being 0, which is x equals negative 2. Is that better?
Yep.
Good. Okay, so let's look at the g of x, which is x the square root of 9 minus x squared. I have the same question here. I'm asked to find critical numbers, but I don't have the domain. I have to find the domain of this function first. How come that I didn't do it here? What is the domain of any polynomial function? All the numbers. They are not creating any problems. But I have to find the domain of this function. Can anyone tell us what to write that will lead us to finding the domain? I have to solve and get the domain. What do I have to write? Say it again. No. To find the domain. No one likes the square root. I just don't know why. No.
So
Yes?
you have to make 9 minus x squared equal to, like,
9 minus x squared.
yeah, equal to 0 and see which way is positive. After that,
Say it again. Greater than or equal to 0. That is the condition of existence of the square root. The square root will not exist if the quantity under the square root is not greater than or equal to 0. Now, if the square root is in the denominator, I cannot say equal to 0. But it's not in the denominator. So first I have to solve this. How do I solve this? What type of inequality is it? How do we call it? Say it again. Right, which degree? Yes, but 2. So it's quadratic. How do I solve a quadratic inequality? What do I have to do first? You cannot take square roots in an inequality. That's not allowed ever. Unless we are told that everything is positive. So, for example, 4 minus 1, is this greater than or equal to 0? Then I will separate it if you want to, and then I can take the square root because they are both positive. But here I have no idea what x is. So I cannot do this. No, first of all, I have to arrange it in descending order. Then I see that it has a negative leading coefficient. What do I do then? So this, we are solving a quadratic inequality. Then I multiply both sides by -1. What happens next? Say it again. But what happens here? I multiply both sides by -1. Yes, I completely agree. And yes, I have to factor. Perfect. How do I factor x squared minus 9? X minus? Good. Very good. So now I have to study the sign. I have x minus 3. I have x plus 3. And I have x minus 3 times x plus 3. We're studying the sign of this expression. Study exactly what we did with the particle situation. We studied the sign of the velocity. Study the sign. Good. So when is x minus 3 0? So indeed, -3 and 3. So I have to put them in ascending order. So x minus 3 is 0 under 3. And x plus 3 is 0 under -3. What about the product? What happens under -3 for the product, or to the product? Of course. And what happens under 3? Perfect. Good. So now what is the sign of x minus 3? It's a linear function with a positive slope. Or plug in numbers. If you don't want to think in these terms, from negative to 0 to positive, then just plug in numbers and tell me the sign. Excellent. On the first subinterval, I multiply two negatives. Sign.
Positive.
Excellent. On the second subinterval, I multiply a positive and a negative.
Negative.
And of course, positive. This is what I want. Which sign do I pick? Which sign is less than or equal to 0? Only one sign is less than or equal to 0. Which one? Yes. So the domain of this function is between -3 and 3. Say it again. Ian, can you ask the question one more time?
No, it wasn't a question. I was trying to answer your question.
Okay, is it clear? No, is it clear what we just did?
Yeah.
Any questions? Anyone? Any questions? Okay, so all this work had nothing to do with the critical numbers in a way, but it had everything to do with it. I needed to find the domain of the function. So the domain is -3 to 3, and the function is g of x equals x the square root of 9 minus x squared. Good. So now I start from scratch. I go back to the question, and the question is asking me to find critical numbers. Okay, what is the first step towards finding critical numbers? I'm sorry? Yes, we found the domain. All this work was to find the domain. So yes, we will find the derivative. Very good. How do I differentiate this?
That is equal to 1. Should be like 1/4.
The first function prime is 1 times the second function, plus the first function times the second function prime, times the inner function prime. Okay? The only thing I can do is simplify 2 with 2, nothing else for now. So I have the square root of 9 minus x squared minus x squared over the square root of 9 minus x squared. Of course, I need to find the least common denominator. That's the reason why I said in the previous chapter, you will see why we will have to fully simplify each expression till the end. This is why, right here, right now, for the critical number. So since the least common denominator is this, I have to multiply the top of the first fraction by it. So can anyone dictate the numerator? Very good. Very good. All this work was to find the derivative. I haven't even reached the stage of finding critical numbers yet. So I will factor out -1. This is -2x plus 9. So 2x squared minus 9 over the square root of 9 minus x squared. All this work was only for finding g prime. Are you okay with the g prime? Any questions, please? Any questions on g prime? So now, critical numbers come from two sources. From f prime of x being 0, or from f prime of x being undefined, when f of x is defined. Can anyone identify immediately or on the spot what are the critical numbers from f prime being undefined where the function is defined? Where is this function undefined? Exactly. Because we did not have this situation before. The square root was in the numerator. It was defined everywhere between -3 and 3. But now it's in the denominator. It cannot be 0. So two critical numbers, x equals plus or minus 3, come from this situation. Exactly that the example that I gave you with the square root of x. So the square root of x is defined on 0 to infinity. But its derivative, which is 1 over 2, the square root of x, is not defined at 0. Perfect. So now I still have critical numbers coming from f prime being 0. When is a fraction 0? When is a fraction 0? Exactly. When 2x squared minus 9 is 0, which means x squared equals 9 divided by 2. I move 9 divided by 2, and I take the square root. So x equals plus or minus the square root of 3, the square root of 9 over the square root of 2, or x equals plus or minus 3 over the square root of 2, and I would rationalize. So 3 the square root of 2 over 2. Critical numbers. So this function has 4 critical numbers. 2 coming from f prime being 0, these 2, and 2 are coming from f prime being undefined where the function is defined, and these are the 2. Any questions? Any questions? Okay, I would like to come back here and discuss these so we can put them in. Absolute max, a function f has an absolute or global max at c, absolute or global max at c, if f of c is the maximum value of f of x. There is nothing more than that. F of c is the maximum value of f of x. Now, what would you say about minimum? So in other words, we will say that f of c is greater than or equal to any f of x, in other words. So the absolute minimum function f is absolute or global minimum at c if f of c is the minimum value of f of x, which means f of c is less than or equal to any value of f of x. By extreme values of f, we mean max min. That's what we mean. Or called extrema. So if you see in a problem, test, quiz, final exam, find the extrema of this function, you are asked to study the function and find all possible max min, local, relative, absolute, global. That's what the extrema means. Local max. A function f has a local or relative max at c if I can show that interval. So if f of c is greater to f of x near c. Local min, a function f has a local or relative min at c if f of c is less than or equal to any value f of x but near c. So these two are talking about the open interval. If I cannot show the open interval around c, then that is not a local.